Imagine you are sitting on a recliner chair watching your favorite movie on a lazy Sunday. Now your mom calls out your name and asks you to run some errands. You can imagine how difficult it would be for you to get up and do the work. Imagine you are practicing for your 100 meters race on this track and somebody asks you to stop immediately within a second. Will you be able to do it? What if you are asked suddenly to run towards the right? Will you be able to turn immediately? The answer to both of these questions would be a no. You can stop, yes, but gradually. You can also turn, but not sharply. And guess what? It's the same story with every object. Every object will continue to do what it's doing. If it is at rest, it will remain at rest. And if it is in motion, it will stay in motion. But what can change this? Only an unbalanced force can change this. If it is at rest and an unbalanced force acts upon it, it will move. If it is in constant motion and an unbalanced force acts on it, it may accelerate or change direction. And this is nothing but the Newton's first law of motion. An object at rest stays at rest, an object in motion stays in motion, in the same speed and in the same direction unless acted upon by an unbalanced force. In simple words, it means that objects continue to do what they are doing unless some external unbalanced force acts on them. We can also understand this using a simple diagram. If the forces are balanced, there can be two cases, an object at rest or an object in motion. If the forces are balanced, there can be two cases. An object may be at rest or an object will be in motion at a non-zero constant velocity in a particular direction. This can be the only two cases when forces are balanced. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. Newton's first law of motion says that an object will continue to do what it's doing until it is acted upon by an unbalanced force. Now, what happens when there is a net force acting on an object? That's precisely what the second law of motion will discuss. Do you remember understanding the first law of motion with a simple diagram? If the forces are balanced, the acceleration will be zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. That is, only if the net force is zero. Now let's try to create a similar diagram for the second case. If the forces are unbalanced, then there will be acceleration. On which two factors do you think the acceleration will depend on? Okay, let's say there is an object on the table. You apply a force of 10 units on it, and then you apply a net force of 20 units on it. In which case do you think the acceleration will be more? Of course, the one in which the force was more. So we can say that one of the things the acceleration depends on is net force. If it is more, more will be the acceleration, and if it is less, lesser will be the acceleration. Now let's say there are two objects on the table. One has a mass of 3 kilograms and the other has a mass of 5 kilograms. Now if you apply the net force of 10 units to each of them, which one do you think will accelerate more? Surely it's a 3 kilogram one because it has lesser mass. Less the mass, more will be the acceleration. More the mass, less will be the acceleration. Hence we can see that acceleration depends inversely on the object's mass. Mathematically, it can be written like this. In simple terms, the acceleration is directly proportional to the net force supplied and inversely proportional to the mass of the object. That's the second law. The net force is the product of mass and acceleration. With this, can you tell me the unit of force? The standard unit of mass is kilograms and that of acceleration is meter per second square. So the unit of force is kilograms times meter per second square, and that is what we call as Newton. 1 Newton is 1 kilograms times meter per second squared. If the mass of an object is 10 kilograms and the acceleration is 10 meter per second, then the force will be equal to 100 newtons. We can say that 1 Newton is defined as the amount of force required to give 1 kilogram of object and an acceleration of 1 meter per second squared. What happens when you place an object on the table? The object exerts a force on the table, exerts an upward force on the object. There are two forces that result from this interaction: a force on the table and a force on the object. The magnitude of these two forces are same, but the direction are different. These forces are called as action-reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we see here is nothing but the display of Newton's third law of motion. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of the force of the first object equals the magnitude of force on the second one. And whatever the direction of the force, the direction of the force of the first object is opposite of the direction of the force on the second one. For example, a frog swimming. When a frog is swimming, it pushes the water back and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is only the object here and there is no second object. But that's not correct. The wings of the bird push the air downwards and the air pushes the bird upwards. Action-reaction forces make it possible for the birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You are right, it exerts a forward force on the bullet, and the bullet exerts an equal and opposite force on the gun. And it is called the recoil of the gun. A perfect example of Newton's third law. If the force exerted by the gun on the bullet is as same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as bullet, right? Same magnitude of forces but different acceleration. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is product of mass of the object and acceleration, or acceleration is equal to force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than the mass of the bullet, and hence the acceleration of the rifle is less than that of the bullet. If you are in a boat and step out of it into a land, there are two forces involved. you pushing the board and the height of the board pushing you forward. And that's why you see the board goes behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship, and the ship also applies a force on the sailor. But do you think ship will accelerate as much as a sailor? Not really, and I think you know why. To understand inertia, we need to look at Newton's first law again. Here it is. In simple words, this means that the objects tend to keep on doing what they are doing. It's the natural tendency of every object to resist change in their state of motion. If they are at rest, they would prefer staying at rest. And if they are moving at a constant velocity, they would want to continue doing so. This tendency of objects is called nothing but inertia. It's the natural tendency of the object to resist change in its state of motion. Yes, you already knew what inertia is, and yes, Newton's first law of motion is also called as law of inertia. Do you think all the objects have same inertia? All objects resist changes to the state of motion, right? So all should have the same inertia, correct? Well, not really, because inertia tells us how strong is the object's tendency to resist the change in its state of motion. Think of it like this. There is a tiny brick kept on a table next to a relatively larger and heavier brick. Which one do you think would be easier to push? Without doubt, it's the tiny brick. Right? But why is that? It's because the heavier brick's tendency to resist change in motion is more. The heavier the object, the more is the tendency to resist change in motion. The more mass an object has, greater will be its inertia. So if we apply equal force to both of these bricks, the tiny brick will be moved further as compared to larger brick. The heavier brick has more inertia. How could we relate inertia and mass? Inertia is the tendency of an object to resist changes to its state of motion, and mass of an object is a measure of its inertia.